Well, hello, everyone. Thanks for joining us on this talk about additive manufacturing today. My name is Derek Schaefer. I'm a PhD graduate student at Penn State University in the Material Science and Engineering Department. My research focuses on precipitation hardening stainless steels and the additive manufacturing of those steels and how it impacts the properties of the steels and how it impacts the following heat treatments as well. So my expertise is really in metals and metallurgy, with AM and welding type of processes specifically. So I think I'll be able to bring a lot of information to that part of our discussion.
Yeah. Greetings to one and all present here. Myself, Kiran, and I'm currently pursuing my bachelor's degree in metallurgical engineering. And thanks for Derek and Tilak for coming forward for this podcast. And yeah, we will discuss some points on additive manufacturing.
Hello all, myself Tilak Chakravarti, and I'm currently pursuing my master's in medical technology program, and I primarily work on metallurgy and as well as blood repellent coatings and biofouling coatings, and currently we are looking to develop some blood repellent coatings for endoscopes. And basically we are looking additive manufacturing as a process which is going to help us in prototyping the products pretty easily, and my expertise comes from magnesium, which I have worked in my bachelor's as well. So let us start the podcast with asking some understanding about what is AM, how it's different. So, Derek, what do you think about additive manufacturing? Why do you think it has gone to its phase of now being the technology which is revolutionizing not only manufacturing but also the other space of the technology as well?
Yeah, so I think AM has grown to the heights that it's grown to so far because of a couple reasons. One is the incredibly fast turnaround time, especially with you can think of like a steel part or a steel casting or something like that. Rather than having to get the steel in the size that you want and then take stuff out, you can build it up from the ground up in layers, and that's really powerful if you're thinking about like rapid prototyping, or you're thinking about quick turnaround times in manufacturing, or even situations like I know in a couple cases, like factory floors will have a single AM unit and they'll use it to produce replacement parts for when something else in the factory breaks, rather than having an entire warehouse full of backup parts. And I think that that's exceptionally powerful for a manufacturing technique. Along with that, AM presents you the opportunity to do things such as input internal structures without having to then weld structures shut at the end and things like that. The part that comes to mind, the one that everybody always talks about, is the GE LEAP fuel nozzle that has an internal structure. They're all created by AM processes now, and they all have an internal structure that actually increases the fuel efficiency of the fuel nozzle. And that is really only a capability of AM. You wouldn't really be able to produce that part through traditional means. In the last thing, and kind of, I believe you're talking about like bio applications, and the last thing that I think it's really taken off in is the bio atmosphere, where you can customize these parts for a person. Everybody talks about customizing parts or rapid prototyping parts for like an industrial application, but ultimately humans are each one of you is unique. So having that customizability aspect of the manufacturing technique in a matter of seconds, just by changing some stuff on the computer program, is a very powerful tool. Now, that's not to say that AM doesn't have its weaknesses. And my perspective of AM is all in metals, because that's just what my research is in. So like in general, the weakness of metals is this idea of the feedstocks and the cost of producing the parts. So like if you're going to do a high batch number, a lot of these parts, like such as in the automotive industry, a lot of times the cost is astronomically high in comparison to what you would normally expect through traditional manufacturing techniques. But I think that there are some companies that are working on that issue as far as like the production rate, and that's something that I would be interested in talking about in a bit. I wanted to know if you guys had anything else to say about that, what you guys think are some interesting aspects of AM that have allowed it to take off.
So Kiran, like when you look at your studies and you are introduced to AM, so what is the first thing which you get fascinated about when you look at additive manufacturing?
Yeah, additive manufacturing is one of the growing technologies and definitely a industry 4.4 technology. Yeah, I am like looking forward to work on it in future as well. One aspect which interests me in additive manufacturing is the rapid customizability with additive manufacturing. As Derek said previously, rapid tooling, rapid prototyping, all of this process can be done very quickly in additive manufacturing compared to conventional manufacturing processes. That time gap which we reduce is one of the major key advantage in mass production. So if there is like any way where we can implement rapid customization and produce a lot of parts through additive manufacturing, that would definitely lead to a great developments. Yeah.
And one thing which I like to add here is that additive manufacturing has become a very, a kind of robust technology because it exploited all the other technologies which is happening in other space like computer science, in situ monitoring, and image processing techniques. So wherever the other technology has grown, it has came to additive manufacturing because additive manufacturing itself is a kind of an multidisciplinary field where you have everybody's work to be contributed to improve the AM techniques. And in the recent years, every other fraternity of the science and technology has came into the field and they have really developed it. And now we can able to get FDM printers, which is like very less cost, and the kind of materials now we are able to operate and the kind of accuracy we can able to get is it's very very good. And as the patent of the structures has been expired like 5 years before, which they have for FDM technology, now we can able to see a lot of players in the market are coming up with new machines for ATM as well, and hopefully in the future we can able to also see these machines for metal manufacturing too. Yeah,
Mhm.
so that's what I want to add here, and we can move forward with the questions of powder bed fusion techniques. So I think Derek could have been a great person to talk about powder bed fusion. So let's start with Derek.
Yeah, so most of my work is in powder bed fusion of precipitation hardened stainless steel, and it's actually interesting because so my work is on like the material science side of it and what the properties of the steel are after processing. So I have a great idea of what the material is going to do after powder bed processing, and some of the processing parameters and things like that. But I also have worked up at Sim3D, which is a like kind of partnered with the university through the Applied Research Labs at Penn State, and they have a lot of good researchers, grad students, and faculty members who are doing stuff like in situ monitoring techniques to monitor the system. A lot of them is with direct energy deposition, but they're also looking at powder bed fusion as well. And then, I also have a couple members of my group who are doing modeling of powder dynamics in interactions. So it's interesting to kind of see everything. Although my research focuses on the back end of it, it's kind of interesting to get, all the sides. But I think that for those who don't know, powder bed fusion is essentially you lay down a layer of powder and then you trace whatever shape you want to build in that layer with a laser, and then the table moves down and you scrape over another layer of powder and you hit that with a laser in whatever shape you want that layer to be, melting it to the layer below it. What's interesting about powder bed fusion in comparison to something like directed energy deposition, where we would melt the melt pool with a laser and then inject powder into it, building up that material, is mostly dimensionality. Powder bed fusion allows for much smaller pieces, much smaller characteristics of the pieces, and better surface finish overall. Usually with DED, what ends up happening is you have to machine away stuff at the end. With powder bed fusion, most of the parts are like fairly applicable. You can use them mostly right away. Obviously, in some like high impact situations or places where you can't really have very many issues with your parts, such as like aerospace, you still have to do some post-process finishing. But I think powder bed fusion is like the closest we have in metals to parts that are ready to go right out of the machine. Now, I think the main barrier to powder bed fusion is I think it's a little bit slower as far as the build time goes compared to like something like DED, because you're not putting down as much material at once. But when you take out the post-processing stuff, it ends up being about the same. But also is this powder consumption idea. You put in this powder and you're really only making your part out of part of it, and then all that extra powder kind of goes to the wayside. So there are a lot of groups looking at powder recycling as well. And then, but when you compare that to something like DED, where you're shooting the powder straight to the melt pool, the capture efficiency of that powder is much higher. And then you compare that to something like wire additive manufacturing, where you're melting a wire directly onto the part underneath it, which is essentially 100% capture efficiency. And powder bed fusion really kind of looks lackluster in that compartment compared to those other techniques. But I think the recycling aspect of it kind of redeems it a little bit as far as that goes. Did you guys have any like specific questions or anything that you thought that I should mention or discuss with respect to powder bed?
Actually, the post-processing, as you told about in aerospace and other applications, it demands post-processing, and I get it that they wanted to be 100% sure that the product is completely fine. But in some cases, additive manufacturing, as a technique, as a technology, has its importance when it comes to straight away production. You have to, not go through any steps of the traditional manufacturing and just shoot up your actual product and make a use, right? So in such areas, where do you think that the elimination of post-processing is what everybody aims for, and where do you think that the technology is moving in that direction?
I mean, that's an interesting question, because I think everybody wants to eliminate post-processing as much as they can because it saves them money and it saves them time. Mm-hmm. But there are, like, especially when you're considering post-processing, including things like heat treatments, there's a ton of post-processing that usually has to happen. And when you think about it, if you were going to take like a raw material compared to the additively manufactured material, you would probably at some point in your production do the same heat treatments. People often forget that, especially in powder bed fusion DED with metals, it's a fusion-based process, so you're completely melting the material and resolidifying it. So you're not really always going to get the microstructure and the properties that you want in that material directly out of the machine. It's the same thing that if you were to cast a part, you're not always going to get the microstructure you want directly out of casting. You often have to heat treat it after that. Now, there have been cases shown, and actually in some of my work, we were able to show that additive can actually like do things to your material sometimes that actually improves the properties, because the solidification happens so fast, and because it's slightly different, solidification modes and stuff. But a lot of times that actually decreases your ability to then post-process it. You're, if you have an insanely high hardness, it becomes very hard to machine or grind or things like that. So I think that, the post-processing heat treatments aren't going to go away. I do mostly precipitation hardening stainless steels, and you're just not going to get the precipitation part of that alloy, which it's designed for, without heat treating it afterwards. So everybody wants to build it and take it out and use it, but it's designed to be heat treated, and you're not going to lose that by additively manufacturing it. As far as like machining or polishing the parts, I think that in a lot of applications, like in a lot of general industrial applications, I don't know that that's that critical. I know that, there's been a lot of work in reducing defects inside the material. And I think that we're getting to the point where like we're pretty on par compared to like wrought products as far as defect or inclusions, things like that. But the critical issue in some of these parts for like aerospace applications or high fatigue applications is that surface finish. And I know there's one professor at Penn State that's doing post-processing stuff where I forget exactly what the term is for. You guys might know. where you have like a bin that vibrates abrasive particles, and you put your part in there for a certain amount of time, and it vibrates the particles and stirs the particles around that part, and it actually comes out very nice, very well polished and very smooth, while maintaining the geometry that you wanted. So that's all stuff that like I don't see it going away. I actually see, especially companies who want to use AM more, actually probably looking into it in more detail, because you need to have it. But I think that you know, the desire is, I build this part in this machine, pull it out and use it. But I don't see us getting to that. I would actually not be surprised if people started to somehow incorporate some type of post-processing into the process, just so they didn't have to make it multiple steps. But I don't think that the actual process, the actual manufacturing part of that is going to go away.
I totally agree in that point. As you said, there are some materials which has been designed to get heat treated to get the best of properties out of them. In such cases, you can't eliminate the post-processing. But as you said, we can able to get the post-processing into the process, so that we are not investing much money on separate machineries and equipments for post-processing, like hard isostatic pressing unit, where it's going to equally cost the huge amount of the same additive manufacturing machine you're going to buy.
Yeah, so, yeah. I didn't even mention hot isostatic pressing. That the HIP process really throws a loop in things when people are taking it out and then putting it in HIP and then bringing it back. And I know, like with my precipitation hardening stuff, a lot of times the HIP process is totally separate. So they'll take it out of the AM machine, they'll go HIP it, then they'll come back and then they'll do the solution heat treatment and the aging heat treatment. So you're doing like 4 steps just to get to that final properties. Now, I do think that we're getting to the point where HIP isn't always necessary. I think that a lot of places have introduced HIP as a standard technique for like creating baseline, uniformly created parts with minimal defects, because it collapses all those pores on the inside. But I don't know that in most cases that's totally necessary. Like aerospace, I can kind of get it, because you want to be 100% sure that it's not going to have any defects. But in a lot of generic applications, I don't think that's totally necessary. But
got it. Kiran, so what's the next question we are going to discuss about, Kiran?
Yeah, we can. I would like to add some points regarding powder bed fusion and HIP. Regarding the powder bed fusion, I think we also do some selective melting over the bed, just to make sure that the layers don't fuse together and those stuffs. That is, we selectively melt the first layer for the second layer to fuse. Then upon that, we keep on building. And I think that powder bed fusion is a breakthrough for additive manufacturing of metals, since it was not possible by like SLA or FDM technology. And regarding the HIP, Derek, do you think that we can use cold isostatic pressing as well instead of HIP?
I mean, I think that I think that you could try. The problem with metals is that they're really strong. So trying to cold isostatically press, it's either going to take a really long time, or you're going to have to use really insanely high pressures. The other aspect of HIP, excuse me, that people often forget is that having that high temperature allows for atomic diffusion into the pores, and you essentially get not only the compression from the gas, but you get a pseudo creep mechanism that actually helps facilitate densification of the part. So the heat, as well as just speeding it up, like actually plays an important role into the mechanisms behind the densification. So for metals, I don't really see people going the cold isostatic pressing. I would be surprised if I saw somebody try to do that, but
I think we can next go to like just discuss about something about SLA and FDM, and then we can get into powder bed fusion in detail. Yeah. So, what are your opinion on SLA and FDM? Do you think that we can print metals using FDM? I did some research and found out that certain companies are trying to implement FDM for metal. That is, they have let's say a wire system where the outer layer is basically plastic and the internal layer being metal, and trying to implement for metal 3D printing.
So I've seen a couple researchers and a couple of companies trying to do this. So if you're thinking of just metal, absolutely not. You're never going to get an FDM machine hot enough to do that. But with this idea of creating a composite wire that either has a metal wire on the inside with polymer on the outside, or I've seen also where they will infuse a polymer wire with metal powder, and then essentially you FDM your part, and then you sinter it and vaporize off all the polymer. Again, when we go back to this idea of post-processing, now we're introducing more steps because we have sintering and we have vaporization of the polymer. So like, yes, it's possible. I know that, what's the company called? They're based out of Boston. I have a keychain. I can't remember what they're called. But they kind of do the same thing, is they create, these fully dense, I don't know how they measure fully dense, but they claim they're fully dense metal parts using FDM. And you essentially have a tabletop unit, but then you also have to have the furnace specially suited to do the sintering and stuff. So I think it's possible. I don't know that it's going to take off like powder bed fusion and DED has. Powder bed fusion is just so direct. You pour the powder in, you upload your part and let it go for a couple hours, and then it's done. With DED, it has so many applications as far as especially with like repair applications. It's nice, this idea of having the FDM system be like a tabletop system. I could just have it here on my desk running. There's no high energy lasers. There's no high energy arcs or anything like that to worry about. But I still have to have the industrial strength furnace to then use it. The one thing I have seen in FDM, as far as like composites go, is they'll make an FDM part that's like polymer with like a carbon fiber along the length, or like a fiberglass strand along the length of the polymer strand. And what that does then is your polymer part is reinforced by a directional composite fiber. And I've seen that to me is honestly more promising than than the metal stuff, because you can use that FDM part right out of the machine, and it's going to already be stronger than just the polymer by itself. But in the same note, and I think that this could be interesting, is I've seen where they take both those technologies and combine them, and they will take a carbon fiber strand that will survive the sintering temperature of the metal, and they'll run it along the length of the polymer, as well as pack it with metal particles. You FDM your part, and then when you sinter the metal, it sinters around that carbon fiber. So now you have a metal part reinforced by a continuous carbon fiber. And I think that like idea of making metal matrix composites in that fashion is very interesting. I think that I don't know exactly what the properties would be. It'd be kind of touch and go with, like, you think of carbon dissolving in steels and stuff like that. So kind of depend, but the concept is there. The concept, I think, would be interesting to play with, but I don't think industrial scale, I don't think it's going to take off as much as powder bed fusion and DED.
That's very interesting when you talk about the composite part, just because FDM, in my way of looking at it, is that it's very, very good for making composites. And when you have to make different materials and you have to sinter it, or you have to have some functionalized properties, I think FDM could be the first go for anybody to try it out. And I think in a lot of spaces where we have to definitely think about is that in metal, a lot of people look into the conventional space and they are actually trying from additive manufacturing to manufacture the products which gives you the conventional properties. But when you look up it now, people are trying to exploit the properties which you get from AM straightly, that you don't have to worry about the conventional part and what are the properties it has, but you exploit the technology which you have with the AM, make your product in that, and you utilize it for the particular application. Because we are now exploring the different applications which could AM solve, which is very promising in a lot of spaces, especially in bio. When you look at it, the surface roughness, which is a problem in metallurgy manufacturing, is actually kind of an advantage where we have here, because the cell adhesion to the surface roughness is very high, which you need. Suppose you go for an scaffold which has to be help the patient to recover from a fracture. In such cases you need surface roughness and open porous structures, which is additive manufacturing is very easily you could able to manufacture, so that the kind of recovery of the patient is very good. So when you have an application which additive manufacturing can be the key solution to such applications, I think we are looking at a very, very promising technology here.
Yep, totally agree.
Yeah.
I think geometry is one of the strongest positives about AM as far as like structural property or structural geometry. Like there are some weird shapes that you just can't get any other way, and I think that it's going to continue to get used for that because there's no other way to make it.
Yes, exactly. So yeah, Kiran, we can move on.
Yeah. So now we can discuss about SLS and SLM and the significance, the pros and cons, and yeah, you can share your opinion on that.
Okay, so in my world, SLM and powder bed fusion are the same thing. People use and I'm going to go on my little rant here because I can. The SLM machine is a commercially available product. Like SLM is a company, and I forget what national lab it started out of, but it started out at a national lab based out of the US and turned into this company that produces powder bed fusion machines. Now people use SLM generically to describe the process, but what they're talking about is laser-based powder bed fusion and calling it SLM, which yes, selective laser melting, I guess, is describing the process that's happening, but at the same time, you're not talking about a commercial machine from SLM, so it gets a little confusing. So what our group does, and what I hope other groups at least think about doing, is if you're using an SLM machine from that company, you can say that you're using an SLM machine to do powder bed fusion. But I'm hoping that overall, the industry standard is kind of that they use the word powder bed fusion to describe the actual process, because otherwise it gets a little confusing. And in the metals world, we hate the term selective laser sintering because if you're in a powder bed fusion or an SLM type of machine and you're hitting that powder with a laser, you're not sintering it, you're melting it. Even if you're only partially melting it, you're melting it. So even if you're melting the outside and it's sticking together and you still have powder particles in there, it's still melting. Sintering is a totally different thing. And maybe in ceramics or something, selective laser sintering is a thing. I'm not sure. But anytime we come across a metals paper that says they did selective laser sintering and then they show a powder bed fusion part, my advisor just says, what the hell? What the hell are they doing? What are they talking about? I don't know. They're not sintering. So, I think the terms are used fairly interchangeably, but I just need to get on my soapbox a little bit and talk about that. As far as the actual processes go, I think for ceramics specifically, I think there is a difference, and I have no idea about the pluses and minuses of either one for ceramics. Do you guys have any experience in ceramics?
Related to ceramics, one thing which I wanted to tell here is that actually now the kind of physical integrity of the ceramics, as we all know, it's not that good when you intended it for any application as such. But ceramics, where it has taken a very very huge kind of thing towards its filtration processes. A lot of ceramic filters, like in castings, and you can take about any kind of chemical industries and things like that. They require very very geometrically dynamic filters, which is they could able to have a very clear process of what they're intended to do. So in that cases, AM is a very promising approach to manufacture all these products, and you don't require very high machineries, because once you make a ceramic block, machining out of it and you can getting into a final product is very very challenging when you look at it in a conventional way. So in additive manufacturing, you can able to have a small machineries and small equipments, and you can still manufacture the product which you're intended for. So that's what one thing I think I'd like to add here.
Yeah. Cool. Yeah, I have heard presentations about like printing ceramic filters and polymer filters and stuff using AM, and I think that's very interesting.
Yeah, yeah.
So now can we go ahead. Yeah.
Yeah, so let's just move on to the EDM process, which I want to touch upon. And EDM is more restricted to the GE company, because they have bought the whole technology and it's getting a bit proprietorship there. But still, EDM is one of the most you could say a defect-free kind of additive manufacturing technique, because the whole process is taking place inside a vacuum, and you can able to manufacture products in the total setup, which would definitely be a very good choice for reactive materials like titanium. And now people are trying to manufacture magnesium as well. And one of the powder manufacturing company, if I remember, they are actually now trying to make magnesium powders, so that they could able to manufacture products of magnesium as well. So what's your take on that, Rick?
As far as E-beam in general, I think that it's another powerful tool. It's, in my eyes, it's essentially just another power source. I lump it in there with lasers and gas metal arcs and all that kind of stuff. Yes, I think the idea of producing it in a vacuum is interesting, and I think that'll lead us into our next topic as far as like production atmospheres. But I also think that E-beam can be a little finicky sometimes, but so can lasers, honestly. Gas metal arcs are a little bit more consistent, but at the same time that they're more consistent, they are also way more energetic and can, they melt larger portions of the metal, I guess is what I'm after there. So you end up with like, you can't do powder bed fusion with a gas metal arc. It's just not precise enough. So I think the other advantage to E-beam is that the spot is much smaller than in powder bed fusion, so or in laser-based powder bed fusion. So again, you're increasing that dimensionality, decreasing that step size and things like that, improving your parts. I think that the thing I've seen about E-beam really the only concern I've seen about E-beam is that since you have to run it in a vacuum, sometimes you can actually lose some of your alloying elements as far as metals are concerned. So I believe this is obviously not my field exactly, so this is probably in the back of my head. So if I say something wrong, people in the comments or whatever can feel free to correct me. But one of the studies I remember reviewing was this idea that in Ti-6-4, which is 6 aluminum, 4 vanadium inside of balanced titanium, the aluminum content will actually go down substantially when produced via E-beam, especially if the temperature is too hot, because it'll vaporize the aluminum very rapidly because the melting point of aluminum is so much lower, and because the vacuum decreases the overall partial pressure during processing. So, but other than that, like, I think that, E-beam's a fine product. Like you said, commercially, it's kind of essentially owned by GE. I think GE bought Sayaki, right? So if you're looking for an E-beam machine, you're probably going to go to GE for one. But I think that's another interesting route. I think it's lumped in there in my head with all the other power sources. So most of my stuff's with lasers, but I'm also not on the processing side, so I don't actually like play with the laser very much. But
one thing which I like to add here is about the loss of alloy content is that you have to have a core-sized, a powder particle in EBM, because as you said, we are using vacuum here. We use very small powders. There's a chance that the powder could be able to lift off from the bed, and also we are using an electron beam here. So generally, what happens is that the particles become negatively charged. So when there are two negatively charged particles, which is smaller in size nearby, it will try to repel and it will try to push off. So which could actually form an electron cloud onto the bed, which might able to add to the loss of alloying element, which Derek just talked about.
So normally, from what I understand, what they've started doing is the plate that you're forming this on is grounded. So that's supposed to be where the electrons are going to avoid the charging issue. And any particles that aren't attached to that bed will charge. So what they've started doing is before they start shooting the electron beam down there, they will actually scan a laser over it real quick to essentially fuse the whole powder bed loosely to the platform. So that way, when you hit it with the electron beam, you don't get powder particles scattering, and you get electron transport to the ground. So I think that it is an issue if your preheat isn't adequate, but I think overall it's not. I think it's becoming less of an issue overall. I think a lot of people are looking at that as one of the primary issues in EV.
So I think this then takes us to our next question of the atmospheres that's involved in AM. So Derek is the guy who has to go on this as well. So let's ask Derek about it. So how much important do you think this atmosphere is, like when you talk about metal additive manufacturing?
Yes. So I guess I could talk mostly about my research here is again, it's in steels, and it's actually about how the atomization gas can impact your microstructure. Now, the atomization gas and the gas during processing the atmosphere is different. And we've actually been able to show that the atmosphere gas, like nitrogen versus argon, actually doesn't play that much of a role. You pick up a little bit of nitrogen, but it's not so much that it actually changes your structure and properties in comparison to the atomization gas. And that's simply because of the kinetics and the behavior of the material in both atmospheres. Your melt pool, when you're actually making your part, it's so small and so liquid for such a short period of time, it doesn't have time to react with the nitrogen and pick it up. But when you're atomizing the powder for use in AM, it's liquid for a little bit longer, as well as re-sterilizing and everything. So it actually has more time to grab up that nitrogen. And we were able to show, we measured the composition before and after additive manufacturing of the powder and of the final part, and we showed that there wasn't substantial nitrogen pickup, but the powder atomized in argon versus the powder atomized in nitrogen had a significant difference in nitrogen concentration. Now this obviously changes when you change material system. If you're doing like a titanium, it'll pick up nitrogen like crazy, and you're not going to want to use nitrogen at all ever, because you'll form titanium nitrides all over the place and it would be terrible. So you're going to want to use argon regardless for processing and atomization. If you're even doing gas atomization, most titanium powders are prep powders, which is a totally different process. We could do a whole nother podcast on powder production techniques, but just saying in general, when you're considering processing atmosphere in general, it is important to use an inert gas for your processing atmosphere to avoid oxide formation. Especially iron and titanium, they'll grab up oxygen real fast. Titanium can actually react fairly explosively to oxygen. So you definitely want to use, an inert environment. As far as which inert environment you're using, for like steels, what our group has kind of found is that the difference between argon and nitrogen processing the atmosphere is fairly irrelevant. Nitrogen can result in a little bit of nitrogen pickup, but not enough to totally change their microstructure and properties or anything. More of what's driving that is your atomization gas, which you can essentially, if you don't even know what your powder atomization was for like a steel alloy, what you can do is look at your nitrogen composition on the spec sheet when you get it, and you can pretty easily tell by what your nitrogen levels are, whether it's around 0.1 or whether it's around 0.01 as to whether it was nitrogen atomized or not. Now for like I was saying, for like titanium, you're obviously not even going to consider using nitrogen. So you're going to probably use argon. But when you get to like E-beam, where you're using a vacuum instead of an inert gas type of environment, your consideration becomes more of a vaporization of alloying elements rather than an addition of some alloying element.
Yeah.
So these are all just things that you need to think about if you're planning on building some kind of part, and you're trying to figure out what inert gas you're buying or what kind of system you're going to run it in. These are the things that you kind of need to think about. And as well as like the shielding system itself. So in powder bed fusion, a lot of times it's in an enclosed box and they essentially just fill it with whatever inert gas you're using. In E-beam, obviously, if you're pulling a vacuum, it's in a vacuum. The whole box is sealed and pumped down. But when you're talking about like DED, you'll want to use a shielding gas as well. But a lot of times those systems, like they're getting to the point where they attach them to these giant 6-axis robot arms and stuff like that. You're not necessarily going to have a nice enclosed box that you can just fill with inert gas. So what you have to do is make sure that you have some type of ample shielding gas set up. I've seen where they use like, you can think of like almost like an umbrella where the actual deposit occurs under this umbrella, which they then like fill with whatever the inert gas is. Just stuff like that is what you need to consider as far as the gas pickup. But overall, like I think people are more worried about the atomization or more worried about the processing gas than they need to be, especially with steels. It has a little bit of an impact, like I said, but overall, like not as much as people seem to think it does. We're actually talking about writing what we call a viewpoint paper, which is like a literature review, but it's pointing out the issues in the literature, because there are quite a few papers out there that, you know, draw conclusions without ample evidence for the conclusions they draw, and it's fairly misleading. And then other people read that and they continue researching on that and cite the previous literature as to why something's happening, but in reality, that's not actually totally true. So I think if I've learned anything in grad school so far, it's that you have to read the literature with a bit of a skeptical eye, because while everything's been reviewed by peers, it's not all good. There is some bad literature out there. So just keep that in mind if you're doing a literature review, trying to come up with something.
So I think I should ask one more question to Derek. I think in terms of career options, like what do you think additive manufacturing is offered going students who is interested in pursuing additive manufacturing as their studies?
That is a great question. So Penn State actually just started, not to do like an ad plug for Penn State here or anything, but Penn State actually just started the last couple of years an additive manufacturing master's program, where you can come for, I think it's 2 years, and take a series of classes specifically about the science of additive manufacturing and additive manufacturing feedstocks and all of the different aspects, from the actual process to monitoring to properties. So, you know, a student coming out of that program is going to be in very high demand because there aren't very many programs like that. Penn State is very well suited to set up a program like that because of Sim3D and the partnership with the Applied Research Lab. But not all universities have such a large amount of experts in additive manufacturing at their campus. So, having Penn State have all these people here and have this program, you can think of this student leaving here, and essentially any place that wants to do AM is going to want to have them, because they're going to be able to tell, like, as an average material scientist, you might be able to add something in about, you might be able to introduce something about to workers, I guess is what I mean, about what your material properties are, what you can do to improve it in general, but you might not know anything about monitoring. You might not know anything about the machines. You might not know anything. You might not have a background in AM. Whereas when you leave this program, you're actually going to have this larger, more direct understanding of what machines are out there, what capabilities do these different machines have, how do I run the machines, things like that. So I'm imagining like a national lab who wants to do AM research and has PhDs who can do the material science side of things or understand the high level scientific part of it, but they need somebody who has experience in all these other aspects to run the machine, to maintain the machine, to offer advice every once in a while about, where they could pick up powders, different powder size options, composition issues, whatever. And I think that if you're looking for a career in AM, even if you say you don't have a master's in AM, say you have, a bachelor's in metallurgy or a bachelor's in material science or something, and you're looking to get into AM, I think one of your best bets, honestly, is going to a national lab where you would probably be one of the people who runs the machine or, helps facilitate research at the lab, or getting involved in a company that uses AM, such as GE. I think it's in Pittsburgh or just near Pittsburgh that they have a plant where they do almost entirely additive manufacturing. I think they have like 40 machines or something like that running all the time. And so if you're looking for a career in AM and you want to be on that side of it, you could be on the running the machine side of it. As far as like doing research in it, you're probably looking at least a master's degree. So that way you have, the graduate level background of the stuff that's happening in the AM processing. I chose the PhD route because I'm thinking about maybe teaching, but also I really like research. So even if I go into industry, I want to be able to be sure that I'm like facilitating research and kind of leading a research program wherever I go. The other important thing to realize is that AM, metal AM, and welding are essentially the same thing. Metal AM is just welding over and over and over again on top of each other. So if you're interested in AM, there's a pretty high likelihood that you would be interested in welding research. So if you're thinking that you may be interested in some kind of metals related field, just start looking around for jobs at companies that make metal parts. You might find that not only in AM but in the welding and in the manufacturing, you might just enjoy manufacturing in general. But I think that's about the extent of my advice. Obviously I haven't looked for a job yet, so can't necessarily say that I'm looking at anywhere in particular, but
yeah, thanks Derek. It's a very good way of putting it into an overall dimension of what you can do from additive manufacturing. So Kiran?
Thank you so much. Thank you so much for joining, Derek. I would like to appreciate both of you. Thank you so much for taking your time and coming over here to have a discussion on additive manufacturing. I do think that the viewers will find it very insightful. We just got it, and hopefully we will continue in the future as well and get into powder bed fusion 2D.
Yeah, absolutely. I think that this was a great discussion. You guys asked some really good questions and stuff, and I would love, like I said, I could do a whole nother podcast on powder feedstock. So if you guys ever want to do another one, feel free to send me a message or whatever. And for all of the other people viewing this, I I assume on YouTube or Instagram or whatever. I have a science-based Instagram account called Science Stuff and Things, actually. So you could check that out. I'll put the link in the description down below. And Kieran runs a metallurgy Instagram page called Metallurgy Daily. They post great stuff about just everything you could possibly need to know about basic metallurgy, as well as some fun pictures and videos about different metallurgy things. So check out their page if you liked our discussion, if you're into metallurgy things. I think that you really like it.
Yeah.
Thank you, and it's been a great pleasure to have a discussion with both of you. Until then, I think it's time to take a leave. So we'll meet soon. Yeah.
Right. Sounds good.
Take care. Bye.
Bye.
Yeah,
Thanks,
thank
guys.
you. Bye. Bye.